Okay, so the topic that we are starting today is speed torque characteristics of shunt wound DC motors. We are going to give a lot of time to the speed torque characteristics of shunt wound DC motors. Now, the behavior of shunt wound DC motors and separately excited DC motors is almost similar if the supply voltage is held constant. So many challenges to overcome. How does it start? Up here. एक काम करेंगे मैं अटेंडेंस दे दूंगा और इस पर वीडियो अपलोड होगा वो वीडियो देख लें ठीक है मैं अटेंडेंस दे रहा हूँ अभी क्लास चालू है ठीक है अभी बात नहीं कर सकता दे दूंगा हाँ ठीक है अभी आई मैंने क्लास ना हो ओके ठीक है यू वॉच द वीडियो लेटर Okay. So where were we?
So shunt wound motor.
Yes. Shunt wound DC motors, the behavior is exactly similar to separately excited DC motor, especially if the supply voltage is held constant. So whatever we are studying, that holds true for separately excited DC motor as well. Now, whenever you come to DC motor, any DC motor, it always follows three relations. Okay. What are those three relations? The first one is an equation, and that equation says that the applied voltage is equal to the back EMF plus the IARA drop, or V is equal to E plus IAR. And I think all of you know this equation, correct?
Yes, sir.
Yes, sir.
I'm showing the diagram. Okay. Actually, I needed more time to draw a better diagram, but still it can do. So this is the DC shunt wound motor. This is our applied voltage or supply voltage, that is capital V. This is the field winding that is connected in parallel with the armature, and it is also in parallel with the supply. So the field winding, this is actually the field winding. It has some resistance that will be the resistance of the shunt field. Plus we are inserting an additional variable resistance in series with the field winding, so that we are able to vary the field current if required. Okay, here. Yes.
Yes, sir.
Yes, sir.
Yes, sir.
This here is the armature of the shunt motor. The voltage developed across the armature, that is called as the back EMF of the motor. And if it is a generator, it is the generated EMF. If it is a motor, it is the back EMF. And the polarity of the back EMF will be such that it will always oppose the applied voltage. So if you are connecting the applied voltage like this, the back EMF polarity will be upper terminal positive and lower terminal negative. I have the habit of using single-sided arrows. I use single-sided arrows. Some people use double-sided arrows. But if you see foreign books, generally they use single-sided arrows. The advantage of using a single-sided arrow is that you do not have to specify the polarity separately. Here, the arrow head is positive and the arrow tail is negative. Is that clear to everyone?
Yes, sir.
When this applied voltage, this is the positive terminal and this is the negative terminal. If you use a double-sided arrow, then you don't know which is positive and which is negative. Then you have to write here, this is positive and this is negative. Okay? But if you use a single-sided arrow, the arrowhead is positive and arrow tail is negative. Okay, so this is the armature of the DC shunt motor. The voltage generated across the armature, that is called the back EMF of the DC motor. Okay, we are going to denote the back EMF by capital E, and the polarity of the back EMF will be such that it will oppose the applied voltage. This armature will have some resistance also. In the book that we are following, that resistance is denoted by capital R suffix ARM. RR. And there is again a variable rheostat, variable external rheostat connected in series with the armature. And this rheostat is denoted by capital R suffix RH. Okay, the suffix is clear. Armature resistance, capital R suffix ARM, and external rheostat, capital R suffix RH. Okay. Yes or no?
Yes, sir.
Yes, sir.
This side we have the back EMF. Upper terminal is positive, lower terminal is negative for normal motoring operation. The back EMF is denoted by capital E. Okay. So if you apply KVL in this circuit, this is the armature current IA. There will be some current flowing here, that will be the field current, and this current will be the supply current given by armature current plus field current. So if we apply KVL in this circuit, the equation that we get is V is equal to E plus IA into V is equal to E plus IA into R. Okay, where V is once again the applied voltage, E is the back EMF, IA is the armature current, and R is the armature circuit resistance, which includes the armature resistance as well as the external rheostatic resistance connected in series with the armature. Okay, is that clear? Yes or no?
Yes, sir.
Okay. So R is the
Yes,
total
sir.
resistance of the armature circuit, that includes the armature resistance plus the external rheostatic resistance. Now this back EMF that appears across the armature, that is given by E is equal to K phi omega. Achha, before that, as I was saying, any DC motor always follows three relations. The first one is V is equal to E plus IAR. What are the other two?
So E is equal to K phi omega.
Yes, the second one is the back EMF is proportional to the product of flux and speed, or E is proportional to phi into omega. Okay, and the third one is
AM phi IA. Or
Torque equal to
torque
K
is,
phi IA.
torque is proportional to the product of flux and armature current, or torque is proportional to phi into IA. Okay, so the three relations are V is equal to E plus IAR, E is proportional to phi into omega, and torque is proportional to phi into IA. Now, if we are using the SI system of units, only if we are using the SI system of units, then if we remove the proportionality signs, then E is equal to some constant, some proportionality constant multiplied by phi into omega, and torque is some proportionality constant multiplied by phi into IA. If we are using the SI system of units, both the proportionality constants are same. That is why we can use the same constant, which in our case we are going to use K. Okay? If we are not using the SI system, then we have to specify different constants, KE, KT, like that. So the back EMF E is expressed by the equation E is equal to K phi omega in volt. Let us say this is equation 2. You know the equation for this back EMF is given by phi Z NP upon 60A, correct? Yes or no?
Yes, sir.
Generated EMF of a DC generator or back EMF of a DC motor is equal to phi Z NP upon 60A. If you remove n from there, write it in terms of omega, then this proportionality constant K is given by Zp upon 2 pi A. What is Z here?
Number of conductors.
Number of conductors is the
Pole.
Number of
number of poles. And what is A?
Number of parallel paths.
Parallel path.
number of parallel paths.
So, is this K a constant?
Yes, sir.
Yes. Once the motor is made, K is constant. Until you design the motor, you can change the value of K. But once the motor is designed and manufactured, the value of K becomes constant because you are neither changing the number of conductors, neither you are changing the number of poles, and nor are you changing the number of parallel paths. And you cannot change 2 and you cannot change pi. That is why the coefficient K is a constant which depends on the design features of the given motor. Okay. Phi and omega are the magnetic flux per pole in Weber and the angular velocity in radian per second of the motor respectively. Okay. Any questions till here?
No, sir.
So if we substitute equation 2 in equation 1, B becomes equal to K phi omega plus IAR. If we substitute equation 2 in equation 1, B becomes equal to K phi omega plus IAR, or omega is equal to B minus IAR upon K phi. Let this be equation number 3. Okay. This equation gives the speed as a function of armature current. This relation, omega is equal to some function of armature current, is sometimes termed the speed or electromechanical characteristic of the motor. Okay. It is also known as the speed characteristic or the electromechanical characteristic of the motor, because on one side you have electrical terms and on the other side you have mechanical terms. Okay. Now for a DC shunt motor, torque developed by the motor is given by torque is equal to K phi Ia Newton meter. As I told you, if we are using the SI system of units, both the proportionality constants are same. That is why we can use simply K. Otherwise, you have to specify KE and KT separately. Okay. So if you substitute this equation number 4 in equation number 3, that means instead of Ia, we substitute Ia is equal to P upon K phi. We get omega is equal to B upon K phi, P upon K phi minus P R upon K square phi square. Okay, is this clear?
Yes, sir.
Now, if the applied voltage is constant, the value of phi will remain constant for a DC shunt motor. When the supply voltage remains constant, the value of phi will remain constant for a DC shunt motor. That means this term K phi again becomes a constant, so that K phi can be denoted by C. And then this equation becomes omega is equal to B by C minus P R upon C square, where C is equal to K phi. Okay, the coefficient C is constant and independent of the load. If the shunt wound motor, if the supply voltage of the shunt wound motor is constant, and if we are neglecting the armature reaction. Okay, when is C constant? When is C constant? When the supply voltage of the motor is constant and Yeah.
Nature flux we are assuming to be constant.
Yes, that means we are neglecting the armature reaction. And you all know what is armature reaction, correct? Yes or no?
Yes, sir. Yes, sir. Yes, sir.
You have joined.
Yes, sir. Yes, sir.
Sure. So this is the equation that defines the speed torque characteristic of a DC shunt motor. Whose equation is this? Is it the equation of a straight line, or is it the equation of a circle, or is it the equation of an ellipse, or parabola, or hyperbola?
Straight line, sir, means negative slope. If I will take omega on y-z axis and torque on x-axis, it is the straight line, negative slope. So
Yes.
it is
That means this is an
speed is
equation of the
equal to
form y is equal to mx plus c. Correct?
Yes, sir.
Yes, sir.
Okay, what is y?
Yes,
Y
sir.
is omega. What is m?
R by C square.
R by
Minus R by C.
minus R
P
by C
upon
square.
k square phi
Minus
square.
minus
No,
r upon
r upon k square phi square. Sorry.
minus r upon k square phi square. Okay.
Yes, sir.
Very importantly, the slope is negative.
Yes.
That means when the torque will increase, the speed will decrease. And we will increase the load on the motor. The load torque will increase, the motor torque will also increase, and the speed will decrease. Okay? So the slope is negative, given by minus r upon k square phi square. Is the value of the slope very high? Is the value of the slope very high?
So less, very less.
Very small if there is no external resistance, because the armature resistance is very, very small. Correct? So if there is no external resistance, then the slope is very, very small. However, by adding external resistance in the armature circuit, we can increase the slope of the line. Okay. X is capital T, and C. What is the value of C? The value
V
of
upon
C
K
is
phi.
V upon K phi. Generally, what do we call this C?
No load speed, sir.
No. When you are given an equation y is equal to mx plus c, what do you call c?
Y-intercept.
It is called the
Intercept on
y-intercept.
y-axis.
That means it is the point where the line will intersect the y-axis. Okay. There is one basic thing. You see two resistances here. One is the field resistance and one is the armature resistance. Okay. Will both the resistances be high?
No,
Or
sir.
both the resistances will be small?
So field resistance will be high and armature resistance will be low.
Why?
Armature resistance small, sir.
Why? Why?
Sir, to maximize the armature current.
Okay. Anyone else?
So field resistance is very low and armature resistance is high.
Your motor will break if you do that.
Sir, armature
The
resistance
field
small, sir.
current required is very less compared to the armature.
So number of turns in the field winding.
Yes, number of turns in the field winding is also more.
See, there is one basic principle. Okay, that is why I came to this diagram back. I came back to this diagram. There is one basic principle that is always followed everywhere in electrical circuits. Why do you think resistance of ammeter is ideally zero and resistance of voltmeter is ideally infinite? Why is it so?
Loading.
So that the armature, the ammeter resistance cannot affect the current and voltmeter resistance cannot affect the voltage.
Correct. So the basic thing is whenever you are adding something in parallel, its resistance ideally should be infinite. Whenever you are adding something in series, ideally its resistance should be zero. Okay? So your field winding is connected in parallel with the supply. Okay? So its resistance ideally should be infinite. In practice, it will have a large value. Whereas your armature resistance external resistance we are connecting in series with the armature, so its resistance should be small. Okay. So coming back to the equation, omega is equal to V upon K phi minus T R square minus G R upon K square phi square. We have seen that this is the equation of a straight line having slope minus R upon K square phi square and having the y-intercept V upon K phi. So I'm going to try and draw this diagram, speed torque characteristic of a DC shunt motor. Okay. On the x-axis, we are in the motor, so the independent variable is torque, and the dependent variable is the speed, omega. Okay. So, initially, we take the torque at 0. If we take the torque as 0, the speed that we get, that will be the no-load speed, and that no-load speed is given by V upon K phi. So when the torque is 0, let us say this is the no-load speed given by V upon K phi. Now, if there is no external resistance in the armature circuit, your armature resistance is very, very small, and so the slope of the line is going to be very small. Okay, so this is, we can say that this is the characteristic. It will become too small. I'll increase it a little. Okay. So let us say this is the characteristic with no external resistance in the armature circuit. Its y-intercept is V upon K phi. Its slope is negative, given by R upon minus R upon K square phi square. Is this clear? Yes.
Yes, sir.
Okay, so this is R1 that is equal to the armature resistance. Now, if I add some external resistance to the armature circuit, what will happen?
Slope will decrease. I mean, the curve will further go down.
Yes, the slope will increase, but the slope is negative. Okay, it will increase, but it is negative. Will the y-intercept change?
No, sir.
No, sir.
So let us say this is the characteristic with some resistance R2 that is greater than R1. If we further increase the resistance, again the slope increases. Some resistance R3 which is again greater than R2. If you go on increasing the slope, what will happen? At some point, your characteristic will touch the torque axis.
Torque axis.
If you further increase the slope, it will touch the torque axis even earlier. Is it possible to have these type of points?
So above 3 can possible, but here speed is 0, means motor stops by adding the resistance. We are means adding the resistance. We are controlling the speed of the motor by adding the external resistance in the armature circuits. So here speed is means slow, it is going down. Here it is showing speed is going down. Here a motor stops, means this is the critical value of the resistance. Armature resistance should be uh, less than this value.
Okay. Now, the question is it possible to have these type of points? Yes or no, in actual practice?
No, sir. I think, sir, up to R4 we can determine.
R1, R2, R3.
Yes.
And R4.
This one is R4.
Yes, sir.
You can determine this.
Yes, sir. This
Why
will
not
be the.
R5?
Sir, actually, at this point, the speed is 0. So practically we can't determine that. And
Sir,
up to
after
R4 it is the
Practically, you can determine and you have determined.
sir,
Tell me,
because
tell
the
me where you have determined.
motor is from forward motoring to reverse
So in
plugging.
block rotor test, we
Yes,
have
block
determined.
rotor test, you find the speed, you find this point for the induction motor. Similarly, you can find the point for the DC motor also. Okay, you block the
okay, sir.
rotor so that its speed becomes 0 and you find the torque. Okay, and
Okay,
this point can be shifted to the left by further increasing the armature resistance. Okay, is this clear, everyone?
yes, sir. Yes.
Okay. So this is your no load speed. Where the torque is 0. The no load speed is given by V upon K phi. And the initial characteristic, the first line, there is no external resistance. Only the armature resistance is present in the circuit. This characteristic is called the natural characteristic of the motor. Is that clear? This term is going to come again and again. Natural characteristic of the motor. What is the natural characteristic of the motor? Is the characteristic without any external resistance in the armature circuit. As you go on increasing external resistance in the armature circuit, the slope of the line goes on increasing. Okay, and the characteristic goes on shifting downwards, but the no load speed remains same. Okay, is this clear? Can I move forward?
Yes, sir.
Yes, sir.
So the no load speed is given by omega 0 is equal to V upon K phi. In this second term, what can we call this second term? What can we call this second term? If we had to give it some name, क्या बुलाएंगे इसको? What will you call it? Will you call it Sumit, Jairam? What will you call it? Anyone? What is that second term? No one?
So R by K square phi square.
T into R upon K square phi square. Not the minus sign, only T into R upon K square phi square. What is that? What can we call that term? This term is the actual speed. This term is the no load speed. What is this term?
Sir, Windows losses, sir.
Speed at load T, torque T.
Speed at
The
load
change
or
of
T.
speed
At
with
torque
respect to torque.
the operating speed.
Operating speed is omega. Operating speed is omega. This is the actual speed, na? Omega is the actual speed. V upon K phi is the no load speed. What is T upon T into R upon K square phi square?
Acceleration.
Speed regulation.
Speed regulation.
Speed regulation.
So speed when the load is increasing.
Like, speed when the load is increasing is omega. No load speed is V upon K phi. Speed when the load is increasing is omega.
Yes, sir. Yes, sir.
Somebody said speed regulation. That was more closer to the right answer. It is basically the drop in speed from the ideal no load speed. Is that correct?
Yes, sir. When the resistance is increasing, it's dropping.
This is the actual speed. This is the no load speed. This is the drop in speed from the no load speed.
No load speed. Yes.
Yes. So this term is represented by delta omega, change in speed from no load to the actual load, and it is given by T into R upon K square phi square. So we can write omega is equal to omega 0 minus delta omega. But what is omega? It is the actual speed of the motor. Omega 0 is the no load speed, and delta omega is the drop in speed from no load to actual load. Okay, clear everyone?
Yes, sir.
Yes, sir.
So in the speed torque characteristics that we have just seen, the uppermost characteristic was the natural characteristic, defined as the speed torque characteristic exhibited by the motor when no at rated applied voltage and rated field flux when no external resistance is included in the armature circuit. Okay. The slope of the characteristic depends only on the internal resistance of the motor armature. So the speed drop on the natural characteristic will be delta omega is equal to T into RARM upon K square phi square. Okay. Where RARM is the armature resistance. And because the armature resistance is very small, the speed drop without any external resistance will be very, very small. However, if you add some external resistance in the armature circuit, then the speed drop delta omega becomes equal to T into RARM plus RRH divided by K square phi square. And now you can control the slope by increasing or decreasing the value of the external resistance. Okay, if we divide both sides of this equation by omega 0, what do we get?
Omega by omega naught equal to 1 minus del omega by omega naught.
Yes, omega by omega naught is equal to 1 minus del omega by omega naught, which can be rearranged like this, correct? Del omega by omega naught is equal to omega by omega naught minus 1.
Yes, sir.
Del omega by omega naught will be 1 minus omega by omega naught, that is omega 0 minus omega upon omega naught.
Yes,
What
sir.
is this del V now? What is this del V? What can we call this?
Speed regulation.
Speed regulation.
Relative drop.
Yes, relative speed drop, or it is the per unit speed drop, you can say. Speed drop in terms of relative units or speed drop in per unit. Okay. Have you seen this type of equation before anywhere? Have you seen this type of equation before anywhere?
Slip.
Yes, it's similar to the slip equation in induction motor, ns minus n upon ns. Slip is equal to ns minus n upon ns. But only the equation is similar. There is no slip in the DC motor like there is in the induction motor. Okay. Okay. We'll stop here. Do you have any questions regarding today's class?
No, sir, but tomorrow you want to take in second half, no?
Yes, I want to take in the second half tomorrow.
Okay, sir.
Timing? Second half
You are
timing?
not, Priya, you are